Welcome, traveler. You found your way to the quiet cosmos, a place where questions drift through the dark and imagination lights the way. I'm J.J. Littleton, your cosmic investigator, exploring the wonders of what is and what might be. Settle in, let your thoughts dissolve, and join me as we journey through stories of fact and fiction beneath the endless night. Every second of every day you are moving, not merely through space, but towards something. Something massive, something hidden, something that might reshape everything we believe about the universe itself. For over 40 years, astronomers have detected an invisible force pulling galaxies, including our own Milky Way, across millions of light-years of space, toward a region we cannot directly observe. It's called the Great Attractor, and the evidence suggests it shouldn't exist. We've built our understanding of the cosmos on the principle that the universe expands uniformly in all directions, that galaxies drift apart as space itself inflates, like raisins in rising dough. But the Great Attractor defies this comfortable picture. It's a gravitational anomaly so profound that it's forcing physicists to reconsider the very structure of reality. What if the universe isn't what we think it is? What if there's a massive concentration of matter, or something far stranger, hidden behind a cosmic veil we cannot penetrate? What if we've been moving toward it all along without knowing? Prepare yourselves. We begin. In 1973, something peculiar caught the attention of astronomers at observatories around the world. They were measuring the cosmic microwave background radiation, the leftover light from the Big Bang that fills all of space, using sensitive instruments designed to detect its faintest whispers. What they found was unexpected. This ancient light wasn't perfectly uniform. There was a slight but measurable asymmetry. The radiation appeared slightly hotter on one side of the sky and slightly cooler on the opposite side. This temperature difference, only about 1 part in 100,000, would have been invisible to older instruments. But with new technology, it became unmistakable. The interpretation was startling. Our galaxy wasn't stationary relative to the cosmic background radiation. We were moving rapidly, at a velocity of roughly 600 kilometers per second, nearly 1.3 million miles per hour, in a specific direction through space. Think about that for a moment. Imagine standing still, believing yourself motionless, only to discover you're hurtling through the darkness at incomprehensible speed toward an unseen destination. The initial assumption seemed reasonable. This motion was simply the Milky Way's movement through space as we orbit our galactic center and moved through the local galaxy cluster. A known phenomenon, a solved problem. But as telescopes improved throughout the 1980s, something troubling emerged. The motion continued even after accounting for all known gravitational sources. After subtracting the pull of the Virgo cluster, the nearest massive concentration of galaxies to us, located about 65 million light-years away, the peculiar motion remained. Galaxies across vast regions of space were all moving in the same direction, converging on a point they couldn't see. It was as though an invisible hand was drawing them together. In 1986, astronomers R. Brent Tully and Richard Fisher published their observations, evidence for a massive concentration of matter beyond the Virgo cluster, located roughly 250 million light-years from Earth.
They called this unknown gravitational source the Great Attractor. But here's where it gets strange. According to our maps of the universe, this region should be empty, or at least not massive enough to exert such tremendous gravitational influence. The visible galaxies in that direction cannot account for the observed motion. It was as though an invisible hand was drawing them together. In 1986, astronomers R. Brent Tully and Richard Fisher published their observations, evidence for a massive concentration of matter beyond the Virgo cluster, located roughly 250 million light-years from Earth. They called this unknown gravitational source the Great Attractor. But here's where it gets strange. According to our maps of the universe, this region should be empty, or at least not massive enough to exert such tremendous gravitational influence. The visible galaxies in that direction cannot account for the observed motion. This realization forced an uncomfortable question into scientific consciousness. Either we were profoundly wrong about how much matter existed in the universe, or we were missing something fundamental about the nature of gravity itself. The evidence forces us to confront an uncomfortable possibility. We inhabit a universe far more mysterious than our theories suggested.
To understand the Great Attractor, we must first understand what astronomers actually observe. And here, the evidence becomes genuinely startling. In the early 1990s, the NASA ESA Cosmic Background Explorer satellite, or COBE, mapped the entire microwave background sky with unprecedented precision. What researchers discovered was a dipole moment, a directional asymmetry unlike anything predicted by standard cosmology. Not only were we moving, but our motion suggested we were being pulled by something extraordinary. Scientists discovered specific gravitational signatures in the motion of galaxy clusters stretching across billions of light-years. Each cluster, each supercluster, showed the same directional bias. They were all flowing toward the same point in space, like streams converging into an invisible river. The scale is almost incomprehensible. Imagine a region of space encompassing hundreds of billions of galaxies, each containing hundreds of billions of stars, all responding to a gravitational influence emanating from beyond the observable veil of galaxies. The cumulative velocity of this great flow reaches 600 to 1,000 kilometers per second. But this represents just one piece of a much larger puzzle hidden in the cosmic structure. In 2016, researchers using advanced galaxy surveys discovered something more ominous: a massive void in galaxy distribution behind the Great Attractor. The Bootus void, a region containing far fewer galaxies than expected, roughly 1 billion light-years across. When combined with subsequent observations, a pattern emerged. The Great Attractor wasn't simply an isolated concentration of matter. It was part of an even larger structure, a supercluster so vast that conventional names seemed inadequate. The Laniakea supercluster, as astronomers named it, contains about 100,000 galaxies and stretches roughly 520 million light-years across space. And at its center lies the Great Attractor, a region of exceptionally dense concentration where millions of galaxies cluster together in gravitational embrace. The most remarkable discovery involves the velocity distribution itself. Every independent survey, from the Wilkinson Microwave Anisotropy Probe to the Planck satellite, confirmed the same basic pattern. Galaxies in our region of space all share a common motion vector, suggesting they're all converging on the same gravitational center. Scientists named this bulk flow, and its magnitude remains one of cosmology's most puzzling observations. The Milky Way, the Andromeda Galaxy, the Virgo cluster, the Centaurus supercluster, all moving together, all pulled toward the same invisible point. The conventional explanation fell short. The known mass in the attractor region could account for perhaps 20 to 30% of the observed gravitational influence. Something was missing, something substantial, something hidden. The evidence extends beyond mere galaxy motions into the realm of the cosmic web itself, the vast network of filaments and voids that constitute the universe's large-scale structure. When we examine galaxy distributions at the largest scales, a strange pattern emerges. The universe isn't randomly distributed. Instead, it forms a cosmic web with galaxies and galaxy clusters concentrated along filaments, much like foam on the surface of a bubble bath. Between these filaments lie vast voids, regions containing almost nothing. The Great Attractor sits at the confluence of multiple such filaments. It's a cosmic junction where multiple rivers of galaxies converge. But here's what keeps cosmologists awake at night. The concentration of matter we observe through conventional methods, counting visible galaxies, measuring their mass, cannot possibly generate the gravitational field we measure. We are off by factors of 10 or more. This gap points toward dark matter, the mysterious, invisible substance that constitutes roughly 85% of the matter in the universe. Dark matter produces gravitational effects we can measure, yet emits no light. It interacts with normal matter only through gravity, making it nearly impossible to observe directly. The Great Attractor might represent one of the largest concentrations of dark matter in our cosmic neighborhood, a dark matter superstructure of incomprehensible scale, visible only through its gravitational influence on the normal matter we can see. Recent discoveries from the Sloan Digital Sky Survey and the 2-micron All-Sky Survey revealed even more structure hidden behind the Great Attractor's position. Additional galaxy clusters, massive filaments of matter, dense regions that suggest a hierarchical structure of gravitational concentration. In 2023, observations from advanced redshift surveys identified what astronomers call the Shapley supercluster flows, evidence that multiple superclusters across billions of light-years all participate in large-scale motions ultimately driven by the Great Attractor's gravitational influence. The most disturbing evidence comes from considering what lies beyond. If the Great Attractor exerts such tremendous influence across our observable universe, what does that tell us about the structure beyond our cosmological horizon, beyond the edge of what we can see? Current observations suggest we might be seeing only the edge of an even larger structure. The gravitational evidence points towards something vast, organized, and fundamentally hidden from direct observation. To understand the Great Attractor, we must reconsider our fundamental model of cosmic structure. For decades, cosmologists operated under the cosmological principle, the assumption that the universe, when viewed at the largest scales, appears roughly homogeneous and isotropic. In other words, the universe looks much the same everywhere, with no special directions or locations. But the Great Attractor challenges this comfortable assumption. The prevailing interpretation among leading researchers suggests that the Great Attractor represents a genuine feature of cosmic structure, a particularly dense region that happened to form through ordinary gravitational processes.
In the early universe, tiny density fluctuations in the primordial plasma grew exponentially as gravity amplified them. Denser regions attracted more matter, which attracted more matter still, eventually forming the structures we observe today: galaxies, galaxy clusters, superclusters. The Great Attractor, under this interpretation, is simply where this hierarchical structure reached an extreme, a cosmic equivalent of a mountain peak towering above the surrounding landscape. Dr. Brent Tully of the University of Hawaii, who first proposed the Great Attractor's existence, envisions it as part of a vast network of structures. The Great Attractor isn't isolated, he explains. It's embedded in a complex web of filaments and voids that extends far beyond what we can directly observe. The physics underlying this structure involves dark matter's mysterious properties. Unlike normal matter, dark matter doesn't interact electromagnetically. It doesn't emit light, absorb light, or reflect light. It exists almost like a ghost, perceptible only through gravity. But perhaps that's where our thinking goes astray. This forces us to reconsider fundamental assumptions about matter itself. What if dark matter isn't a fundamental particle, as most physicists assume, but something else entirely? What if the Great Attractor represents not merely a concentration of unknown particles, but a region where space-time itself possesses unusual properties? Some theoretical physicists, including those working on modified gravity theories like MOND, modified Newtonian dynamics, suggest that perhaps we're misunderstanding gravity itself. Perhaps on the largest cosmic scales, gravity doesn't work exactly as Einstein predicted. Perhaps there's a deeper theory we haven't yet discovered. Leading astronomers remain divided. Dr. Alan Kashlinsky, working at NASA's Goddard Institute, proposes that bulk flows like the Great Attractor suggest we live in a genuinely anisotropic universe, one that has preferred directions and structures that violate the cosmological principle. The universe might be far less uniform than we assumed, he states. Large-scale structures could extend far beyond our current observations.
The mystery of the Great Attractor won't remain unsolved forever. Technological breakthroughs are transforming our ability to map the cosmos. The James Webb Space Telescope, launched in 2021, now observes the universe with unprecedented infrared sensitivity. Unlike visible light, infrared radiation passes through cosmic dust clouds, allowing us to see regions previously hidden. Astronomers are deploying JWST to map distant galaxy distributions with clarity that would have seemed impossible a decade ago. Simultaneously, massive spectroscopic surveys are underway. The Dark Energy Spectroscopic Instrument, or DESI, measures the light from over 35 million galaxies and quasars. Each measurement provides crucial data about these objects' velocities and distances. The cumulative effect creates a three-dimensional map of cosmic structure more detailed than ever before. Recent breakthroughs suggest we're approaching a watershed moment in understanding large-scale cosmic flows. When combined with gravitational lensing observations, where massive structures bend light from distant sources, revealing their presence like an invisible lens, these surveys reveal structure upon structure, layer upon layer of cosmic organization. What technologies might help solve the Great Attractor's remaining mysteries? Several approaches are under development. Next-generation gravitational wave detectors will observe collisions between neutron stars and black holes across billions of light-years. These observations will provide independent measurements of cosmic structure, complementing traditional optical surveys. The Einstein telescope,
currently in planning stages, could revolutionize our understanding of cosmic expansion and structure. Advanced weak gravitational lensing surveys can map the distribution of dark matter directly by observing how it subtly bends light from distant galaxies. The Vera Rubin Observatory, becoming operational soon, will revolutionize this field by imaging billions of galaxies. Predictions about future discoveries point towards several scenarios. Some astronomers predict we'll eventually see behind the Great Attractor using gravitational lensing, revealing the dark matter structures directly. Others suggest the next decade will reveal even larger structures, superclusters beyond the Laniakea, vast cosmic filaments stretching across billions of light-years. The implications are staggering. If the Great Attractor is embedded in even larger structures, structures that extend beyond our observable universe, then the universe's organization might be far more complex and hierarchical than current models suggest. Connect this to broader questions about the universe itself. What determines cosmic structure? Is it simply gravity amplifying quantum fluctuations, or does something else guide the universe's organization? Do patterns repeat at different scales? Could the universe itself be organized according to principles we haven't yet discovered? What this means for us, for humanity, extends beyond mere intellectual curiosity. Understanding cosmic structure is fundamental to understanding our own origins and place in the universe. We live in a galaxy that's actively falling toward the Great Attractor. We're participants in a cosmic flow spanning billions of light-years. We're embedded in structures whose scale defies intuition. The most profound implications emerge when we consider what the Great Attractor reveals about reality itself. First, consider this. If structures as massive as the Great Attractor can exist hidden from direct observation, how many other cosmic structures remain unknown? If gravity from one supercluster can pull galaxies across a million light-years of space, what other invisible influences might be shaping the universe? The Great Attractor forces us to acknowledge that our visible universe, the galaxies we can observe, numbering in the hundreds of billions, represents only a fraction of matter that actually exists. We inhabit a largely invisible cosmos, where dark matter outweighs visible matter by a factor of 5. We are seeing the foam and missing the substance. This connects directly to the ultimate mystery in cosmology, dark energy. About 68% of the universe consists of dark energy, a completely unknown form of energy that appears to be accelerating cosmic expansion. We don't understand what it is, where it comes from, or how it works. Yet it dominates the universe's fate. What if the Great Attractor and structures like it exist within a larger cosmic framework we're only beginning to perceive? What if our universe contains vast regions of completely unknown structure, hidden not behind cosmic dust, but hidden simply because they're so immense that mapping them requires centuries of observation? Some speculative but scientifically grounded possibilities emerge from this consideration. The universe might be organized in a nested hierarchy of structures at different scales. We've observed galaxies, galaxy clusters, superclusters, and now the Great Attractor. But perhaps even larger structures exist. Perhaps our entire Laniakea supercluster is merely a component of even vaster structures. Perhaps the observable universe itself is organized into hierarchical patterns we haven't yet imagined.
If true, this would suggest the universe possesses far more structure, organization, and complexity than current models indicate. We typically visualize the cosmic web as a flat network of filaments and nodes. But what if cosmic structure extends equally in 3 dimensions? What if there are vast cosmic highways, 3-dimensional filaments of galaxies through which matter flows? The Great Attractor might represent merely one node in an incomprehensibly vast network of gravitational organization. Perhaps dark matter isn't uniformly distributed, but clumps into structures we haven't detected. Perhaps the Great Attractor marks the boundary between vast dark matter structures. Perhaps dark matter possesses properties that create gravitational fields in ways we don't yet understand, not through particles, but through something fundamentally different. What if the universe genuinely possesses large-scale structure that violates our assumptions about homogeneity and isotropy? What if there truly are special directions, special regions, preferred axes in cosmic structure? This would overturn our understanding of cosmology and require developing entirely new theoretical frameworks. The most mysterious aspect of the Great Attractor might be what it tells us about what lies beyond our observable universe's horizon. Beyond the cosmic microwave background, beyond the edge of what light from the Big Bang has had time to reach us. If the Great Attractor exerts influence across billions of light years, if it pulls on structures thousands of times more distant than most galaxies, what does that suggest about structures we cannot yet observe? What massive gravitational sources might lie just beyond our cosmic horizon, pulling the observable universe towards an invisible destination? We began our journey with a simple question. What if everything we know about the universe is wrong? The evidence suggests something stranger than that. The universe isn't fundamentally different from what we believed. Rather, it's vastly more complex, more organized, and more mysterious than our theories captured. The Great Attractor is not an aberration or a measurement error. It's a genuine feature of cosmic reality, a landmark in the cosmic landscape, a testament to gravity's power across incomprehensible distances. It reveals that even with our most powerful telescopes, even with decades of careful observation, we are seeing only a portion of the universe's true structure. What we've learned: the cosmos contains hierarchies of structure we're only beginning to map. Gravity sculpts matter across billions of light-years into intricate webs and filaments. The visible universe, the galaxies we can see, represents merely the luminous foam atop an ocean of invisible matter and structure. And somewhere beyond our horizon, beyond the edge of the observable universe, gravitational forces continue to organize and shape matter according to principles we're still struggling to comprehend. What remains unknown? We still don't understand what dark matter is. We don't fully grasp how the Great Attractor formed or what role it played in cosmic history. We cannot directly observe the dark matter structures underlying visible galaxy distributions. And we cannot yet map the cosmic structure beyond our horizon to understand the full context of our universe. The current scientific consensus acknowledges the Great Attractor as real, while recognizing profound mysteries remain. Most astronomers accept that large-scale structure plays a crucial role in cosmic evolution. Many acknowledge that our models are incomplete, that we're missing essential pieces of the puzzle. Yet this scientific uncertainty isn't cause for despair. It's cause for wonder. It's an invitation to exploration.
Somewhere in those mysteries lie discoveries that will transform our understanding of reality itself. We are made of stardust, born from the universe, organized by gravity across billions of years into conscious beings capable of contemplating that same universe. And now we've discovered that we're falling towards something hidden, falling toward a destination we cannot see. The universe is vast, the mysteries are endless, the journey continues. And so, another journey fades into starlight. If you found peace in tonight's story, let it travel with you into your dreams. Until next time, I'm J.J. Littleton, and this is The Quiet Cosmos.